Hi, so hello everyone. Welcome to my talk that is called Proving Macro Expansion with Expandable. First, I'm going to disclose that this talk was supposed to be scheduled on the sidetrack because it's a kind of nerdy side project I had. So it features some kind of advanced Rust stuff. And if you don't want to follow it, it's fine to just get up and leave. So let's start with who I am. So as said, I'm Sasha Pourcelot. I started playing with Rust around 2017. I immediately fell in love with the Rust language. My handle is Scrapsha on the social networks and GitHub. I come from Nice in France. And at work, I'm working at a French company that is called Trust and Soft, and we are building static analysis tools. Mostly for C and C++. And on my free time, I love playing with Rust and building Rust tooling for it. First off, I don't expect everyone here to know what are declarative macros, so I figured I should do a quick 101 about this. The whole point about macros is to have code that is called at compile time by the compiler and that generate codes that is then run at runtime by your program. Declarative macros are used using a very specific DSL. So the idea is you write your Rust macros, along the rest of your program, and the compiler will just understand that there is a macro definition and then replace further uses of this macro with the actual expansion of the macro. Declarative macros have a funny property, which is that they are pure. In a nutshell, this means that macros cannot do nasty things such as opening a network connection or reading files from your file system. Which is very cool because it means that as a macro user, you can totally trust third-party declarative macros. Also, keep in mind this is completely different to procedural macros, which are defined in regular Rust code and are allowed to not have purity and can do any kind of nasty sign effect. And this is also not the same as macros 2.0, which are defined in RFC 1584. This concept of macros 2.0 is a whole new DSL that is just not relevant here. Here is an example of use of a macro. So its name is matches. It takes two arguments, first an expression, then a pattern, and optionally an if clause, and the idea is it returns whether if the expression matches a specific macro. And here is the implementation of the said matches macro. I'm going to go step by step to how it works. So first off, we tell the compiler we are declaring a macro. We give it its name, which is matches. Then there is a macro matcher. This is basically where we explain what are the arguments we expect when the macro is called. So here, first we expect an expression that we will call E. Then we expect a comma. Then we expect a pattern that we will call pat. Then we expect a repetition. This is what the $sigil tells us of 0 or 1. This is what the question mark tells us, token of if, followed by an expression that is named guard, and finally a repetition of 0 or 1, comma. Then comes the macro transcriber. The transcriber explains what the macro should expand to. So here we are matching over the input expression, see if the pattern that was provided matches, and optionally if the evaluation of the guard returns true. And if it's the case, then the whole expression evaluates to true, otherwise it evaluates to false. So this is how matches is implemented under the hood. And the good news is, The good news is it's an actual macro from the standard library. I just explained to you the whole matches macro without changing anything. So even if you don't understand the rest of this talk, at least you know how matches is implemented. Now let's go back to the actual content of the talk. There are a lot of reasons why I love Rust, but ultimately everything boils down to the idea that when my program compiles, I know it always works or almost works. Here is a quick example. So let's take a function that is called vec. It takes as inputs an object that is into iterator and returns a vector that contains the elements of this iterator. What it does is it creates an empty buffer, then iterates over the input iterator, and repeatedly pushes elements to the empty vector, and at the end of the function, the vector is returned. Except I used here an arrow instead of a dot for the call to the push method. And rustc is smart enough to tell us that this is an error and to tell us that we should use the dot operator here. Now let's look at the equivalent of what happens of the same code in the declarative macro word. So once again, we create an empty buffer, then we repeatedly push elements to it, and at the end, we just return it. And what happens is that rustc happily accepts our macro, and this is because macros in Rust are valid even though they may expand to invalid code. So Rust is great because when my program compiles, it works well, except for macros. So with that in mind, wouldn't it be great to have a tool that allows us to check as quickly as possible that a macro always expands to valid code? So this was the side quest I just discovered. From this point, there are two questions that need to be raised. First, what is valid code? And second, what are the limitations of such tool? First off, the notion of valid code would be great if valid code could mean, in this context, code that compiles, except declarative macros often rely on code defined in the very same crate, and it would require a huge amount of static analysis. So perhaps a more realistic target would be to guarantee that a macro always expands to code that is syntactically valid. And for instance, if it is able to prove that all the possible expansions of the macro are part of the Rust language, then it could accept the macro. And on the other hand, if it detects that one or all the possible expansions of the macro do not belong to the Rust language, then it could just reject the macro. Now, let's see what language theory tells us about this very problem. First, the macro transcriber is actually just a sequence of tokens with some repetitions in it. This means it is roughly equivalent to a regular expression. So now we have a more defined problem. We want to detect if the language expressed by the regular expression is a subset of the Rust language or not. Then we can, we can build a state machine from every transcriber. For instance, here we have a state machine that corresponds to the vec macro. So first, we are creating an empty buffer. This is labeled as A, so here. Then we are repeatedly 0 or more times pushing elements to it, which is labeled B. And then at the end of the transcriber, we are returning the buffer, which is labeled C. Now, the idea will be to walk the transcriber state machine using a Rust parser, either until we find a syntax error or we have reached every reachable state in the Rust parser itself. I'm going to give a more formal explanation of this algorithm. So first, let's define the function ft. Ft is a parser, so it takes as input a parsing state and tries to parse the token or sequence of token t and returns the state once these tokens have been parsed. For instance, parsing an arrow right after parsing an expression is an error, whereas parsing a dot right after an expression means we are parsing a field access or method call. F has interesting properties. For instance, not giving it a single token returns the exact same input state, and parsing multiple tokens in a row corresponds to calling f multiple times and composing its results. So the first rule is called the identity rule, and the second one is the composition rule. Then we can try to reason in terms of set of states instead of state. Instead of state. In order to do this, we define the function capital Ft, which takes as input a set of states and returns the set of states after t has been parsed for each element of the set of states. It has the same identity and composition rules as the smaller f. With the definition of capital F, we can define what happens when we are parsing 0 or 1 repetition. Intuitively, parsing 0 or 1 repetition means either parsing nothing or parsing one repetition of the said repetition. And using the identity rule, we can further simplify this expression. This means we know how to parse 0 or more repetitions of something. The next step is to define how to parse 1 or more repetitions. Here we are leveraging the idea that parsing something 1 or more times means parsing it once, then parsing it 0 or more times. And then we are using the composition rule in order to get a definition of what happens when we are parsing 1 or more repetitions that is built on what happens when we are parsing 0 or more repetition. In order to the definition of what happens if we parse 0 or more repetitions is a bit more tricky. It relies on several steps. First, we need to define a quick notation helper. So t to the power of n represents n repetition of the sequence of token t. We also need to define the notion of transition. So a transition is every change that can be observed between two states. We use the difference to show this. So s prime minus s means all the difference in the parser states s prime to s. This includes stack frames in the parser that have been pushed or popped, or local variables that have been modified. Using the definition of transition, we can define the delta t function. So here it takes a set of states as input and returns a set of states. And what it does is it computes the transition that occurs when parsing the token t from the state s. This allows us to compute the value of capital S, which is this horrible equation. I'm not going to detail it, but the whole point of this is to parse enough repetitions of t such that parsing more repetitions will not create any new transition, which means that when we have parsed n repetitions of t, we are sure we have reached every reachable state of the parser. Once we have a value of capital N, we can just we can define the formula of 0 or more repetitions as the union of all the repetitions from 0 to capital N tokens. So this is how we define. This is how we prove that a macro is correct. Now, there is something I didn't explain. It is how we can define the parser itself, how f can be defined. We need to build a parser that is fully interruptible, which means that we must be able to start it, then give it a few tokens, and stop it, do something else, perhaps compare it, and then restart it, give it tokens again, and being able to do this forever. We also need to be able to compute the transition from one state to another. My first idea was to manually define this as a push-down automaton. I did this by manually writing every possible state and every possible transition from one state to another. For instance, here there is the expr start state. It corresponds to the state in which the parser is when it is about to parse an expression. And for instance, if the first token available is a left bracket, then we are now parsing another start of expression, and we push to the stack that we are currently parsing an array, and more specifically, its first element. This worked very well for a very limited subset of the Rust grammar, but as you can see, this was extremely verbose, and the end result was almost impossible to read. So naturally, this just doesn't scale to the whole Rust grammar. My next idea was to write the parser, to write a tiny compiler that allows for a language in which that I will use to write the parser and then compile it to the same push-down automaton I showed earlier. So here is an example of code. This worked extremely well, except compiling to a PDA, a push-down automaton, is not enough. For instance, it's very hard to model the notion of variables in a push-down automaton, which completely removes the idea of function argument and return values. My third approach was to completely ditch the push-down automaton and instead build a custom virtual machine. This allowed me to quickly add support for variable function arguments and return value. The only thing that is truly missing for now is the notion of reference to value, but this is something I could probably add. So all these algorithms I show you are implemented in a crate that is called Expandable. They can be triggered by just slapping an attribute macro in front of a declarative macro. So I'm going to show you how. First, here is my example crate. So the only thing that has changed here is that Expandable is a dependency. Then we have an example code, so you can recognize the vec macro from earlier, and I used the arrow operator here instead of a dot. And and Expandable is distributed as a set of attribute macros, which means each attribute macro corresponds to a specific expansion target of the macro. And as you can see, adding expandable : expr triggers the expandable macro, which in turn is able to understand that the arrow here is not expected and ultimately suggests to use a dot instead. Now I'm going to talk about the limitations of this tool. The first one and most obvious one is that the parser is still very incomplete. It has partial support for expression and doesn't support thread definition, impl blocks, structs, enum, and everything like that. And I will probably continue developing this parser by porting the crate scene piece of code by piece of code. Also, it doesn't work well with recursive macros. What it currently does is just checking that we are indeed allowed to call a macro at the right place in the transcriber. But ideally, we want to check that the macro call in the transcriber matches at least one of the macro matchers. and eventually to check that the corresponding transcriber expands to a specific kind of syntax node that is valid in this context. For instance, we want to check that we want to trigger an error if we are calling a macro that expands to a pattern if it is called in an expression position. There is also what I call macro ruleception, which is when a macro defines another macro during its expansion. This form I show here would be quite easy to detect, except sometimes it can get really tricky and potentially depends on user input, which makes its detection impossible. I don't think this is an issue. I think we can safely suppose we will not pass this because this is actually not much used in practice. That's all for me today. Thank you so much for your attention, and thanks.